So the second section we're going to take a look at this week, 5.1, and this is on exponentials. This is also the last chapter that we do that's really the first part of this class. So this will finish up the algebra part of it, and then chapter 6 will be starting trig. Okay. So let's take a look at those two expressions I have, x squared and 2 to the x. Each expression has a base and it has an exponent. So we want to make sure we know which one is which. In the one that I just circled, what's the base? X and the exponent? 2. In this one, they switch places. The key thing that we look for when something is an exponential function, that's just an expression. It's not like y equals, that would make it a function. But when you're looking for something that's exponential, you're looking for a variable that's in the exponent. That's one of the key things. So just summarizing what we just said. This is not an exponential, the one that I circled in black. X squared. What is that? Yep.
Quadratic.
It's a quadratic, which is a specific type of polynomial. Okay, so that is a polynomial when your base has a letter and your exponent is a number. And for it to be a polynomial, not only does the exponent just have to be a number, but the exponent has to be a non-negative integer. That's how polynomials work. So you might see like x cubed plus 3x squared plus 7. That's a polynomial. Variables in the bases, non-negative integers for exponents. That's a polynomial. When you switch that, so that the variable is now in the exponent and the base is now the number. There is one number that it can't be, and that's 1. But as long as the base is any number other than 1, and the variable is an exponent, that's exponential. Why do you think the base can't be 1? Yeah, if you graph y equals 1 to the x, you're basically just graphing y equals 1. That's a horizontal line at 1. So the base has to be a number other than 1. It can be bigger than 1, and that'll cause something to happen. It can also be between 0 and 1, and that will cause something else to happen. So that's an example of what we call an exponential function. Y equals a to the x. That would be what we would call the base function, or the parent function. There are no transformations in it, no pluses or minuses, no shifting or stretching. That's just the basic exponential function. Now, if we graph it, let's graph we'll pick a number for a. Let's pick 2. So let's graph y equals 2 to the x. And I'm going to do zoom 6. That's what an exponential function looks like. It starts to curve up relatively quickly at a certain point. Before that point, it's usually pretty flat. So what do you think the domain is of that function? It's all real numbers. Yeah, it does go to the left forever, and it does keep going to the right. I mean, it goes up more than it goes right, but it does keep going to the right. So the domain is all real numbers. How about the range? Yeah, it's anything that's greater than 0. From 0 to infinity. Well, I guess I didn't write the range. But in this problem, that's what the range is. It's from 0 to infinity. The domain of an exponential function can never be changed. I don't care if you shift left and right a certain amount, it still is going to go left and right forever. But the range can be changed. Like if I were to take this graph and put a -5 on the end of it, what that -5 did is it shifted it down 5. So now the range is from -5 to infinity, not including -5. It might look like it hits -5 as you keep going to the left, but if you check the table, type in some negative numbers, you can see it's getting very close to -5.
So there is like a horizontal asymptote
Yes.
at the bottom, but not at the top.
Yep. Exponential functions have horizontal asymptotes. Right. Because if you take a number and raise it to a negative power, remember what that really means. It means that. I don't care what negative power you raise this to. If you take 1 and divide by a huge number, it will never be 0. That's why there's a horizontal asymptote.
What's the AE plus real numbers?
So this says A is an element of the real number system. So we're talking about the base. So A is a real number. But the real number that you pick, actually even more specific, it's a positive real number. And it can't equal 1. So when you're talking about exponential functions, the base is a real number. It has to be positive, but it can't be the number 1. Really weird things happen if you try to let the base be a negative number. You can't even graph.
Because wouldn't every other x value be like, because if it was an even, if x was even, then it would be a square. If it was odd, then it would be a cube.
Yeah, we start to get into really, like if you tried to graph -2 to the x, well, if you were making a table of that, when x is 0, you get 1. Anything to the 0 power is 1. But then when x is 1, you get essentially -2 to the first power, which is just -2. But then when x is 2, what's -2 to the second power? 4. So what you're going to end up with is a graph that's going to oscillate positive, negative, but then even weirder things happen, like if you let x be 1/2. Now you're raising to the 1/2 power. And what does that really mean? You're raising to the 1/2 power. That means you're taking a square root. And what's the square root of -2? So now this value is an imaginary. So when you let the base be a negative number, really weird things start to happen. If you type this in, you will not even get a picture. So that's why positive real number, but not the number 1, because that would be a constant. So these are all examples of exponential functions. They satisfy the definition of a positive real number for the base, not equal to 1. You can have pi as a base, that's fine. That's a positive real number, and it's not 1. These are all examples of non-exponential functions. The first two are polynomials. You could think of g of x if you wanted like this. Same. So f of x and g of x are polynomials. And then y equals, it's a combination of a rational and a radical function together. But it's definitely not exponential. Any questions why these top ones are and the bottom ones are not exponentials? So let's look at the difference between 2 to the x and 3 to the x. Just a different base. So I'm going to put 2 to the x. I'll put 3 to the x. And what do you think the difference is going to be?
Once you get into higher exponential.
Once you get into higher values, there's a very big difference by raising 2 to a power compared to 3 to a power. I mean, think of 2 cubed versus 3 cubed. It's already a pretty big difference. One of them's 8, one of them's 27. By the time you get into like bigger and bigger numbers, it's a huge difference. So 3 to the x is going to get bigger faster. So if we graph it, you're not going to see much of a difference to the left. But to the right, you're going to see it curve up sooner. And there's the difference.
Is it ever possible to get just like a straight line upwards for any reason? Just
I mean, I could change the window to make it, like, trick it and make it look steeper than it really is by distorting my screen. But in reality, no, it's impossible to get a vertical line. Okay, so both of those were pretty straightforward to analyze because they were written in what we call like the standard form. You had a positive base and a positive exponent. Well, the base has to be positive. We already said we're not even looking at ones where it's not. But this letter, the exponent, doesn't have to be positive. And if there's a negative here, like that, we want to fix it so that there isn't a negative. Because the negative complicates thinking about it. So we're going to figure out what can we do to get rid of that negative. So from what I showed you earlier, we know that if you raise something to a negative power, it just means put that expression in the bottom of the fraction so you can make the exponent positive. So like a to the negative 3, 1 over a cubed. So we have a way of dealing with a negative number. So we're going to apply that to dealing with a negative exponent. So let's say we had a to the negative x. If you want to think of it this way, there is technically a number between that negative symbol and that x. Right. You could think of it as having a 1. So let me put that step. Let me do it like this. Okay, so I'm copying it to a new page because I need a little more space. So a to the negative x. We're going to think of it as a to the negative 1x. Now, what are you doing with these two things, negative 1 and x? What operation? You're multiplying. There's a rule, I think we talked about it earlier this week, for when you would end up with a product of exponents. When do you multiply two numbers together to get the new exponent?
When you have the exponent around parentheses, that's an exponent.
Yeah, when you have a power to a power.
Yeah.
So when you raise an exponent to another exponent, that's when you would end up multiplying these together. So let's think about what this would have been like before that step. You would have multiplied two things together. You would have had a power to a power. And that's, now I can go back to the other page. You could have had something like that. A to the negative 1 to the x. That's a power to a power. And if you multiply them together, you get negative 1x, or negative x. Now, what's a to the negative 1? If we fix it so there's no negative exponent. A to the negative 1 is 1 over a. So the idea is, if you have a problem that has a negative exponent in it, you can fix it by just taking the value that's the base and flipping it and just getting rid of your negative. So if you had something like, let's say 4 to the negative x, I can get rid of that negative by flipping the base and then just getting rid of the negative. Those are exactly the same. And the reason why that's important is because when the base is less than 1, this is a decay function. This is exponential decay. When the base is bigger than 1, it's growth. You may look at that and say, oh, the base is bigger than 1, it's growth. but there's a negative up here. So that really makes it decay. So that's why it's always important to write it in standard form, which means that an exponent doesn't have a negative. It makes it easier to think about. Any questions on that formula? The other way you could think about it graphically is an exponential growth function looks like that. If you put a negative inside the exponential function, that is a horizontal reflection. That's what the negative does. It reflects it horizontally. So what this graph, I need more room. What it really looks like when you reflect it horizontally is this. Copy of it. Where's copy? Clone. That's what I want. And it's a horizontal reflection. So what you really end up getting is what's called a decay graph. It's a graph that goes down as you go to the right. And that's because of the horizontal reflection of the negative. If you put a negative in front, it would be a vertical reflection. So you can do all the transformations, just like always.
Is it possible to have, the graph go downwards?
Yeah, so you can't put the negative in the base, but you could do something like that. So the base is still positive. So now what you've done is you reflect it horizontally and vertically. So now, if you do both of them, it's going to look like this. That's a reflection horizontally and then vertically on top of it. So yeah, it can basically go any one of those four ways, depending on which reflections you do. Okay, so let's graph these. Just for us thinking about it, how can I rewrite 2 to the negative x so it doesn't have a negative x? 1 over 2 to the x. And again, that number is going to be important in a little bit. So let's graph 2 to the x and 0.5 to the x. You're going to see exactly what I just did by hand on the screen. There's 2 to the x. And the other one is going to be a horizontal reflection. So let's look at them. What's the domain? Just to make it clear here. That was the blue one. That's the red one. What's the domain of the blue one? Yep. But what's the domain of the red one? Yeah, I told you can't change the domain. No matter how you flip it or shift it. If it goes on forever and you shift it, it still goes on forever. So domains stay the same. Ranges, what's that? Oh, I didn't put it in this one. Ranges can change. It depends on what kind of transformation you do. Some transformations change the range, some don't. What's the range of the blue one? Yep, so everything's 0 to infinity. And how about the red one? Same. A horizontal reflection wouldn't change the range. A vertical reflection in this case would. So range 0, you never reach it, to infinity on both. Any question on that? So now let's just think about it in general. Okay, we looked at it specifically for 2 to the x and 2 to the negative x. What doesn't matter if it's 2 to the x, 5 to the x, 12 to the x. That number could be any positive real number except 1. And we would still get the same type of results. So let's think about what happens as we approach infinity, as we head to the right, and we approach negative infinity, heading to the left. We can use the last problem as kind of like a guide to remember what it looks like. a to the power of x would be something like the graph in blue, could be a little steeper, and 1 over a to the x is the general shape of the red one. So, in the blue one, as you head to the right, what happens to your y value? It goes to infinity. As you head to the left, in the blue one, what does your y value get close to? Well, you're heading to negative infinity on the x, but the y value, it's approaching 0. Now, how about for the red one? As you head to the right, what happens on the red one?
0.
You go to 0. How about as you head to the left? We go to infinity. So what we're really looking at here is the difference between exponential growth and decay. You've seen both in that chart right there, graph. So the key difference whether you get a growth or decay is the base. If the base is a number greater than 1, that's growth. If the base is between 0 and 1, it's decay. What if the base is exactly 1? It's a horizontal line. That's neither. What are you even talking about? Okay, so it's either greater than 1 or between 0 and 1. I'm not going to do that. So I could prove to you that 2 to the x and 2 to the negative x are really horizontal reflections. Graphing them and saying they look like horizontal reflections, that doesn't prove they are. I could prove it. And that I was going to show you, but I'm not going to prove it. It's simple. I mean, that's all it is to prove it. It's pretty short. So we can transform these functions exactly the same way we've transformed everything. Here's like a template. Okay? So f of x equals, let's say we had, I don't know, some number raised to, multiplied by a number in front of the x. Add or subtract a number. That's all inside the exponent. So that would be considered inside the function. Then you could multiply by a number in front. And you could add or subtract a number on the end. This is my base. So the numbers I use there, that indicates the order that you do the transformations in. What would adding or subtracting inside the exponent do? Shifts it left and right. It's a horizontal shift. How about multiplying inside the exponent? Or in general, multiplying inside the function. Yep?
Is it a horizontal stretch?
So that's your horizontal stretch. As I've said many times, they're backwards. So plus would shift you to the left, negative would shift you to the right. The bigger the number you put in front of x, the more of a compression you get. The smaller a number you put in front of x, the more of a stretch you do. Okay, how about multiplying by a number outside the exponent? Now we're on the outside. What would that do?
Horizontal stretch.
No, we got the horizontal stretch.
Oh, vertical stretch.
That's your vertical
I
stretch.
thought.
And what about adding or subtracting outside the exponent? That's your vertical shift. If the transformation indicated by position 2 or 3 has a negative, that will cause a reflection, either a horizontal or a vertical reflection. So it's exactly the same as every function we've studied so far. So let's look at this one. It says, list the transformations needed to turn f of x into g of x. Okay, so first of all, how many transformations are happening in g of x?
It's like all three.
3. Yep, there are 3. There is no horizontal stretch or compression in this one, but the other 3 are present. What would be the first transformation you would do? The plus 1, and what would it do? Yep, yeah.
Shift one left.
That's going to shift left 1. So shift left 1. Okay, what's the second thing you would do?
Vertical stretch. So the vertical stretch.
Vertical stretch. Can you tell me a little more?
Switch by 2.
Vertical stretch by factor of 2. And what's the last thing you're going to do?
Vertical shift of vertical shifts right 5. Never mind. Up. That was
Yep.
be down.
Shift down 5. Once you say up or down, you don't necessarily have to say vertical, just like when you say left or right, you don't have to say horizontal. Left, right covers direction, so does up or down. So you need direction and amount. So shift, direction, down, amount, 5. That's the shortest way to say it. And that's it. So if you were to graph this one, what would the domain be? All real numbers. You need to think about it. It's all real numbers. What would the range be? I'd have to figure that out because we've done some vertical stretching and vertical shifting. So we have affected the range in this problem. It's not going to be 0 to infinity. But we could figure it out. I think it would be, I don't think the 2 would actually affect it. I think it would be -5 to infinity, but I would graph it just to double check. Okay, so this is an example where you might have 2 different things, and at first they look totally different, but they're exactly the same. So this would be an example of like you do something on the test and it might be multiple choice. I have one answer listed. Your answer you get doesn't match any of them. Well, maybe it does, but you didn't write it the same way I did. So let's try this one. So the goal is to work with one of them until you turn it into the other. It doesn't matter which one you work with. Let's work with the top one. Does anybody see something I could do, maybe focusing on the exponent first, to start to make the top one look more like the bottom?
You could factor 2 out.
Okay, we could factor 2 out, and I would, yeah?
No.
No, we can factor 2 out, but I would also switch the order because the x should come first. So let's just fix the order. So now at least it's letter, number. That's the same. And we are going to factor something out. Does anybody see what we could factor out? And it would start to make this exponent look more like that one. A -2. If you factor out a -2, you're left with x minus 1.5. Now, you're multiplying here. What would cause you to multiply 2 things together up in the exponent? What must you have had? Yep. Yeah, you must have had a power raised to another power. So think of it this way. And what does 2 to the -2 mean?
1/4.
Yeah, it really means 1 over 2 to the 2. And what is 1/4 as a decimal? 0.25. So we just showed that these two things are exactly the same, but they were written completely different. I would say the better way to do it is the bottom way, because that's standard form where you can see the transformations easily. It's been shifted 1.5 units to the right. This one, all kinds of things have happened. You've got, if you try to think of it that way, it's more to think about because it's not in the standard form. Okay. Any questions on that? Okay. This I don't want to spend a ton of time on. It's kind of its own little separate thing. It's just an interesting graph that has an exponent in the variable, and it has something to do with what we're going to look at tomorrow.
Is this like just to like exit or not?
Yeah, I just want you to look at this graph and just notice something. So if I type it in, and I do zoom 6, I didn't type it in. 1 plus, oh, I didn't have enough. And close it, right? That should be okay now. Let's try that. Okay. So what does it look like this graph has? It does. It has an asymptote. And if you set x min, like let's go negative 40 to 40. So let's zoom out a lot on the x-axis. You can definitely see there is an asymptote. And if you go to your table and start plugging in bigger and bigger values for x, you'll start to see it's getting close to a certain number. Anybody see what number it looks like it's getting close to?
2.72 or 2.71.
Yeah, it's getting very close to this number, 2.71828. Okay, it's getting very close. And if you do it on the negative side, it does get closer and closer to that. Well, the asymptote that's at 2.718, that is not just a random number. Okay, in math, there's a number called e. It's used when we do logarithms. And this particular graph happens to have an asymptote at a special number we talk about when we do logarithms. That's all I wanted you to see there.
Interesting.
So it's kind of a weird idea to think about this graph because you're taking a number that's getting infinitely small, like pretend x is 20,000. 1 divided by 20,000 is extremely small, getting close to 0. And then you're taking something that's infinitely small and adding 1 to it. So you basically have something extremely close to 1, but you're raising it to an infinitely large power. So it's always like there's like a battle here between something's getting infinitely small, but this is an infinitely large power. So what ends up happening? Well, what ends up happening is this gets very close to the number 2.718. And that's a special number that we use in math. So we'll talk more about that number tomorrow. Okay, but that number is called E, 2.718281828. It does not keep repeating 1828. I don't know the next number after that. I forget. But it's not 1828 again. And E is, it's named after someone. It's named after a mathematician. That was his last name? Euler. He's German. So in German, EU, you say it like Oi. So Euler, that was his name. And I don't know why he got it named after him, but he must have done something with it. So E is a number we'll talk about more when we do logarithms. So it's kind of an interesting thing related to having variables in the exponents, which is what we're doing today. And that's all I'm going to say about that. So last thing we want to look at is some formulas. So like if we want to figure out a calculation, say of a city with 50,000 people growing at 2% every year, what would be the population 30 years from now? That's exponential growth.
Nice.
Anytime you have something that's increasing at a percent, that's exponential growth.
Because the percent keeps building on each year.
Right, exactly. It works the same way with banking, right? If you make interest on money, that interest gets deposited in your account, and now when you make interest, you're making interest on the money you had plus the interest they paid you. So it keeps building. Compounds. So we're going to look at the formula to figure out population growth. I think what I'm going to do is this. So this is the formula for figuring out the population of a certain town if it increases at a steady rate.
Is there going to be a question like this on the homework?
Yeah, I think so. Yep, I definitely. We're going to jump right to the result of the formula. So once you get this part copied down right there, you're good. That's all you need. That's the formula you need. Okay, so that's why I said just copy down what's in the bracket, and we're just going to jump to the formula that we use, which is P times 1 plus R to the T.
Yeah, that's a 1.
That's a 1. So this is called the exponential growth formula. It has 3 variables in it. The P is an initial amount. So that could be like the amount of bacteria in a dish, could be the amount of people at the beginning of a city or something, but P is an initial amount. R is the rate of increase as a decimal. So if we're talking about like a 12% increase every year, we need 0.12. Don't put in 12, that would be 120%. And T is the amount of time that has gone by. Now, that is exponential growth. If you change one thing in that formula, then it would become decay. Like if I said to you, the population is decreasing 2% every year. Anybody have a guess what you would change to make that exponential decay? Make the plus or minus. All the variables mean the same thing, so I won't label them again. You know if it's a decay problem if they talk about something decreasing over time. It's a growth problem if they talk about something increasing over time. Now, because we have variables up in the exponent, that's not an algebra 1 kind of equation. If you try to solve something like this, it's not that easy to figure out when you raise a number to a certain power, how do you get 12? I mean, if it was 8, that'd be easier. If it was 4, that's easy. But 12 is not an easy one. So the only way to solve a problem with a variable in the exponent, algebraically, is with a logarithm. Well, we haven't done logarithms yet, so we're going to use graphing to do it. You could put something in y1, and then put something in y2, and look for an intersection. We will talk about how to do it algebraically, but that won't be for today. So we've got a town with a population of 50,000 people, increasing, so we know which formula we should be using, at a rate of 2.5% per year. So step 1, write a function that represents this. Step 2, use the formula to find out when the population will hit 100,000 people. And what I would do to name the y variable, I would call it population as a function of time. So I would use P of t. I mean, I guess you could use a amount if you wanted to be more generic, but this amount is a population of people. So P is a good letter. Okay. What comes first in my formula?
The initial amount.
Initial amount. What was the initial amount here?
50,000.
50,000 times what goes in the parentheses.
1 plus the rate of increase.
So 1 plus the rate of increase. I'm going to put it up above for a second so we can combine like terms. What's my rate of increase?
2.5%. No,
2.5%.
The decimals would be 0.025.
Yep, so 0.025. So that means in the parentheses, I should have a base bigger than 1 because this is a growth problem. If the base is less than 1, then now you're doing a decay problem. So this is growth. And what else do we need?
You need time.
Yeah, I need my t as an exponent.
Yeah, okay.
Not a hard equation to solve if you know logarithms, but right now we don't, so we're going to do it graphically. So there's your function that models the problem. And they want to know when the population hits what?
100,000.
So where does the 100,000 go?
With,
Where is PT?
It goes in for P of t. So put 100,000 equals 50,000 times 1.025 to the t. And there is a little bit of algebra I could do here just to make this easier to type in. Does anybody see something I could do on both sides? Almost like you were solving it for t, but this is really just going to make our numbers smaller to put on the calculator. By what? Yeah, we can divide each side by 50,000. This would be the first step if you were solving it using algebra. I'm doing it, so I have smaller numbers to type in. What's 100,000 divided by 50,000?
20. Just be
2. So essentially, that's the equation you're solving. That's not a very big equation. The thing that complicates it is having a variable in the exponent. So let's graph it and see what we get.
Do we put x or t?
Yes, you have to use x as your variable. So we're going to put a line at 2. We're going to put 1.025 to the t. If you didn't divide by 50,000, that would have been fine. You just may have to adjust your window to go way up to 100,000. Doing it this way, I don't. I can use the standard window, and that'll be fine. I think. Maybe. Let's see. No. So I need to go further to the right. Let's set the x max at like 40. I think that should be fine. Yeah, it's fine. It's good enough. I can see where they cross. So second calc intercept. And I get a time of how many years before the population hits 100,000? Yeah, about 28.1. So about 28.1 years. Now, just be careful if the question says something like the population in 2020 was 50,000. When will the population hit 100,000? Well, you'd have to add that to the year they told you. So if it was 2020, that would be 2048. At some point in 2048, and then a tenth of the way through the year, so that's in what, February? Is a tenth of the way through, I think. So anyway, that's the idea. So just be careful if it asks for a year and not a how many years. This was a how many. We don't know when the population was 50,000. We don't have a year. So. Any question on that? All right, so let's see. When you graph something that's exponential, be careful as always about including negatives. A lot of time, negatives won't make sense because you might be dealing with time, but you might be dealing with an amount of people or an amount of something. Amounts can't go negative if we're talking about like bacteria, people, things like that. So we're going to look at something special now. This is still exponential growth, but it's specifically growth of something double. So let's say we started with 100 bacteria, and then it doubled every hour. Times 0 is what you started. So what did we start with?
100.
How about after 1 hour? How many do we have? 200. And then after 2 hours?
400, yeah.
3 hours?
800.
800. Now, rather than think of it as 100, 200, 400, 800, I want to think of it as something to do with 2 to a power. So think about the original amount and something with 2 to a power. Can you think of how you can write 200 using the original amount and using 2 to a power? Yeah?
100 times 2 to the first power.
Right. This is 100 times 2 because we're doubling to the number of hours that have gone by. So how could we write 400?
Same thing, but 2 to the second part.
The original amount times 2 to the number of hours that have gone by. Original amount times 2 to the third. So, what do you think we would have if t hours have gone by?
But you just replace it with t.
Replace the exponent with a t. So in this case, it would be 100 times 2 to the t. And in general, it's the initial amount times 2 to the t. But the denominator, this is important. You have to divide by the length of the time to double. Because this exponent represents the number of doubling cycles that have happened. Let's say I had a bacteria that doubled every 8 hours. And 24 hours had gone by. How many times has the bacteria doubled? It's only doubled 3 times. You shouldn't be raising 2 to the 8th power. If you raise it to the 8th power, you're saying it doubled 8 times. So if you had a bacteria and it doubled every 8 hours and 24 hours had gone by, you do 24 divided by 8. So that exponent is the number of doubling cycles. Not necessarily the amount of time that has gone by, unless something doubles at a unit rate of 1. Then they'll be the same. So this one, it said a bacteria doubles every 1 hour. So if 5 hours have gone by, it's doubled 5 times. 12 hours, 12 times. The number of hours matches the number of doubling periods. So let's say we had 100 bacteria doubling every hour. So in this case, the number of doubling cycles will match the number of hours. When will there be 350,000? So that's the equation you want to use. And let's fill it in. For that one, I would use b of t, so the bacteria as a function of time. Okay, initial amount. 100 times. You don't have to think about the rate here. If you wanted to think about it from the formula we had before, this is really 1 plus r. That's what that really is. But we're looking at a very specific rate. If something doubles every whatever, but if it's doubling, that's a growth rate of 100%. How would you write 100% as a decimal? 1. That's why there's a 1 here and a 2 there. Doubling means growth rate of 100%. So it's really the same formula as before. It's just a special number here all the time for doubling. Okay, so 100 times 2 to the t divided by my doubling period, which in this case is 1, so I really don't need to divide by anything. So there's your equation. And they want to know when there would be how many bacteria. Yeah, so fill 350,000 in for B of t, and then do a y1, y2, and see where they cross. So this is just like the population of a town. This is just population of bacteria. Is there any question how to do it on the calculator?
What's the B stand for?
I just used B to represent how many bacteria as a function of time. Okay, and if you want a quick estimate, you could go, let's take 100. So that's after 1 hour. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's between the 11th and the 12th hour that we're going to get 350,000. So now I have a quick estimate. I can get my actual answer and make sure that it's 11 point something. All right, so the last thing? Yep. So last thing, well, the opposite of something doubling every hour is something halving every hour. And when something cuts itself in half every hour, or half hour, or minute, or second, that's called a half-life. So half-life is usually talked about in terms of radioactive substances. So if let's just look up half-life something. Let's see. So half-life of uranium. Okay. So I don't know if you can read it or not, but it says that the half-life of uranium is 4.5 billion years. So what that means is, let's say you make a pound of radioactive uranium from a nuclear power plant. You've got 1 pound of waste. After 4.5 billion years, that 1 pound of waste will turn into a half pound. After another 4.5 billion years, that half pound will turn into a quarter of a pound. And after another 4.5 billion years, it'll be an eighth of a pound, and then a 16th of a pound, and then a 32nd of a pound. But it cuts itself in half every 4.5 billion years. So that's a problem with nuclear waste, is that it doesn't disappear quickly. It stays around for a long, long time. Some things have half-lives that are like milliseconds, like something maybe experimental that they're creating, like new elements, things like that. It may only exist for like a microsecond, and then it's gone.
Yeah, I think there's like one element that they created, but it only existed for like a matter of milliseconds. So
it's extremely difficult to study something like that, because even if you could make 2 million pounds of it, it's probably going to be gone in half a second, and you don't even, it disappears. So the half-life is the amount of time it takes for a substance to basically be cut in half. So if something's cutting in half, what kind of growth rate do you think that is as a percentage? It's a 50% growth rate as a percentage. So think about your formula for decay. It's 1 minus r. If something is decaying at a 50% growth rate, that's 1 minus 0.5. What's 1 minus 0.5? 0.5. That's why there's a 0.5 right there. So very similar to your decay or your growth problem, except replace the 2 with a 1/2. Okay, so last problem says we have a radioactive substance that has a half-life of 20 days, and we originally start with 5 grams. So every 20 days that goes by, if you come back and look at it 20 days from now, you're only going to have half of what you started with, because it's, it decays. It's kind of like water evaporating; it just disappears, but it's a little bit. Okay, so let's figure out our formula. What's my initial amount? 5 times 1/2 to the, what's my exponent going to be? T divided by 20. Because if 60 days have gone by, that exponent needs to be a 3, because that's 3 halving cycles, 3 half-lives. So there's your formula. Oh, so that's that part. So that's the formula. And then it says, when will there be less than 5 grams remaining? No, 1 gram. When is there less than 1 gram? So if we put in a 1, and you graph on the left in y1, you're going to get a horizontal line at 1. If you graph what's in y2, it's going to look something like this.
Wait, so what's in the fraction for that second equation?
1/2.
Okay.
At some point, the amount of your substance is going to decay so that it's less than 1. And that would happen right there. So the answer is going to be anything from a certain amount of time forward. Not just exactly that amount of time, but that amount of time and beyond, because it's going to keep decaying. So you'd have to find that intersection point and say that your answer is everything greater than that many days. Any question on that idea? Okay, so that's exponential growth and decay. The only thing we didn't really do was study how to solve them algebraically. That's going to come when we do logarithms. So we'll come back to these equations later. For now, just use your calculator. Okay, so those are the questions for tonight. Mostly just individual problems, a couple ranges, but a lot of just individual ones. Okay, we'll go over that tomorrow, and then we will finish up all our material for the week tomorrow, and then our last test for term 1 is on Friday.